Hi, so this is the second video, part 2 for slide set number 2 in COMP345. This is slide 24 to 50. Here we're going to talk about pointers and references. There's also smart pointers. If you want, smart pointers are going to be in part 3, and that's what you are, if that's what you're looking for. So let me. Oh. Okay, pointers. So pointers, as you may know, is one of the most important concepts to master as you start working with C++. If you don't understand really how pointers are working, you're going to have a very hard time using C++. Okay. Thing is that you can use C++ without using pointers. There's no denying that. But if you don't use pointers, as we will see later, you cannot use polymorphism, which is one of the greatest things about object-oriented programming. So if you think you can get away with not using pointers in C++, you kind of miss half of the beauty of it. Okay. There's a way that you can minimize your use of pointers. Of course, if you don't use polymorphism, don't have to use pointers. Anyway, we'll talk about that much later. So variables, so what are pointers? Variables contain a specific value. For example, a variable that is an integer may contain an integer value. So you have your memory like this. So you have your variable I, which is of type int, and it may contain the value 99. So here's no pointer involved. It's an integer which is named I, contains a value 99. A pointer is a memory cell whose value that it contains is actually pointing somewhere else. Okay. So for example, you might declare this pointer P, whose type is pointer to integer, to reference to the meaning or to indicate something is a pointer, you use a star. When you see a star in C++, mostly, or there's different meanings of it, but when you see a star, it's normally indicating you're talking about a pointer here, if star is associated with a type. So here I have P, which is a variable whose type is pointer to integer. So P contains a value. Yes, there's a value here. The value is the address of a memory cell that it actually points to. If, as in the example here, I'm saying int star P is equal to ampersand I, what is ampersand I? Ampersand I is the address, because each of these memory cells have an address. Ampersand I refers to the address of this memory cell here. So if I go int star P is equal to ampersand I, when I initialize this P here, I say that the value that is stored here is the address of the variable I. So essentially what I'm doing is I'm making this pointer point to this memory cell here. Okay. So that's essentially very simple, but as we will see, that can lead to confusion if you don't use the right terminology and so on. There's a lot of special cases that can be confusing. So it's very important that you understand very well what is a pointer, how it's used, what are the intricacies of pointers, especially when we're talking about objects. Here, there's no stack and heap memory, but it gets even more intricate if you introduce that into your equation. So there are two operators on pointers. The referencing operator, which is star. So as I said earlier, for example, when you have star here, it's basically saying P is of type pointer to integer. However, you can also apply star to P itself, in which case the star has a different meaning here. Here it's to specify a type It's specified that the type is of pointer type, whereas here it's an operator that dereferences P. What's the meaning of dereferencing P? If you go star P, you're actually referencing to the value that is contained in the memory cell that is pointed to by P. That's what's the meaning of dereferencing. You follow the pointer, you get the value. That's dereferencing a pointer. So star P in this case is 99. So if you execute this code here, it's going to output to the console the value 99. Then there's address of operator, which is ampersand. So that's why I use ampersand I here. As I said earlier, if you have I and then you apply ampersand I, what is ampersand I? It's the value of the address of a certain memory cell, which you typically use to initialize the value of a pointer. Okay. Note what I said here. The value of a pointer, the value of this pointer is not 99. That's the value of the memory cell pointed to by the pointer. The value of the pointer is the address of the cell into which it is pointing. Okay. So it's easy to conflate, to confuse these different terms and concepts. Okay. It's also confusing, for example, that star here refers to the type, and here star, if you apply it to a variable name, refers to the dereference operator. Okay, so let's say we have like this here. We have 4 variables which are declared. They're all pertaining to the type int. P1 and P2 are pointers to an int, and V1 and V2 are ints. Okay, so V1 and V2 are ints. What is here should be an int. P1 and P2 are pointers to ints. At this point in time, these pointers here are pointing somewhere, but they are called, because here P1 and P2 were not initialized. Remember when you talked about initialization earlier, P1 and P2 here were not initialized. So what that means is that whatever is the value that was already here in these memory cell, as it was used by a previous process before, there would be values inside of these memory cells. So now P1 and P2 are pointing to the corresponding memory address that corresponds to the values that are already there. Okay, of course, which might be invalid. For example, it might be pointing to a place where a memory space that is assigned to another process, in which case the program will crash if you try to access this value. Okay. Or might give you a segmentation fault, whatever. This is kind of errors that you may have if you use what is called wild pointers. A wild pointer is a pointer that points to somewhere basically where it doesn't make sense. Most cases, you create wild pointers by declaring a pointer and not providing it with an initial value. I'll come back to that later. Then you have what is called pointer assignment, where you assign to a pointer. What is it that you can assign to a pointer? It's an address. So you can take the address of V1 and then assign it to P1. So that's a pointer assignment. Again, on this side here should be a pointer variable, and on this side here should be an address. So you see that there's types that are involved here. This is a pointer to an int, and this is the address of an int variable. Not all of these things are type valid. This one is. So that's essentially sets the pointer variable P1 to point to the address of variable V1. So I had P1 and P2 here that were pointing somewhere where you don't know where it is. Because it's a wild pointer. Now I say, okay, I'm going to assign the address of V1 to P1. And now that makes P1 point to this memory cell here. So you might use different terminologies or terms to explain what's the meaning of that. You might say P1 equals to the address of V1. So P1, the pointer P1, is equal to the address of V1. Or pointer now the P1 now points to V1. Okay. I would say this one is more proper. There's lots of different ways to, verbalize these things. It's very important when you discuss with people that you use the consistent and correct somehow terms as you refer to these things. As I'm trying to do when I give this lecture, for example. Okay, then you can have a value assignment. Now we had pointer assignment, now this is value assignment. So now, for example, I can say V1 is equal to 0. V1 is of type int, 0 is of type int. So I take 0 and put it into V1. That puts 0 here. V1 is now equal to 0. Note that P1 is pointing here. So now, if you dereference P1, then the dereference star P1 is going to get evaluate to 0. So now you see that that's one of the great uses of pointers, that a pointer is something that you create that is peeking into something else, okay? And that you can actually change where it is pointing in time. That's one of the powers of, that's the main power of using pointers. You point somewhere else that belongs to something else, and you can change where it will point as you execute. Then I can also do a value assignment to a pointer variable by using the dereference operator. So essentially here what I'm saying is the value pointed to by P1 is equal to 42. So the value pointed to by P1 is this thing here. It's equal to 42. Now here you see one of the confusing things about pointers. The thing is that here I said star P1 is equal to 42. I never mentioned V1 in this thing here, but the effect is that I have actually changed the value of V1, okay? That's one main reason why pointers can be leading to confusion, okay? Because you look at the code, it doesn't appear you're changing V1, but P1 is pointing to V1. So yes, you just changed the value of V1. So it's powerful, also may lead to confusion. If that's not what you wanted to do really, and then you try to use V1 and it's changed, it's going to be difficult for you to figure out what happened. That's one of the problems about pointers. Very powerful. Possibly if you make a mistake, it's hard to figure out where the mistake is. So P1 and V1 refer to the same memory cell. If you change the value of V1, then star P1 changes. If you change the value of star P1, then V1 changes. Powerful, but possibly problematic if you do a miscomputation or you make an error in your code. So you combine these. For example, you might say, starting where we were before, you might say int v1 is equal to 42, puts 42 here. Int v2 is equal to 9, puts 9 here. Int star p2 is equal to address of v2. P2 now points to the address of v2. Int star p1 is equal to the address of v1. P1 now points to v1, okay? Then you can do a pointer assignment by using these two pointers. So here basically you take the value of P1, which is a pointer, and put it into P2. So now you took the value of P1, which is the address of V1, and then you put it into P2. So now you have three things that point at that contain, that refer to the same value. You have V1 that refers, of course, to its own value, and then both P1 and P2, if you dereference them, they all refer to this same value. And if you change any of these three, star P2, star P1, or V1, it will change all the others. Then you can do a value assignment by, for example, saying star P1 is equal to P2. Star P1 is 42, and then you put it into star P2. And then you basically here what you did is you took 42, which is star P1, and then you put it into V2. Yeah, assuming this here, you put 42 inside of here. Okay, so yes, you can do value assignment by having two dereference operators on each side of the assignment operator. So let's go to more advanced topics. So that's not to say, here I'm just very briefly went over what is a pointer, the concept, and so on. It's very important when you study that you make sure that there's quite a few examples in the labs. I very strongly suggest that you go in the labs and run the examples and then discuss with the marker, discuss with your teammates and so on. It's easy to think that you know what is a pointer and so on, but then when it comes, when you come to coding or in the examination, I might ask you a question that's gonna present pointers from a different angle that you didn't expect. So it's gonna be challenging, okay? So it's all this to say it's easy to think you know pointers, but it can be deceptive. So just pushing it a little further. So you have what's called dynamic variables and local variables. So essentially what's happening, that's what we're going to explain here on the next slide or exemplify on the next slide. So essentially you have, when you execute your program, you have what is called this, the program is using two separate memory spaces. One of them is the stack, on which is stored all the variables that are local to the function that you are currently executing, okay? So there's the global variables, which are at the bottom of the stack. Then when you start the main function, they are the values, the variables that are declared inside of the main function. If the main function is calling another function, such as S1, then comes on top of this another stack frame for the F1 function here. Then F1 itself has P and F1x. And then as you see here, F1 is calling F1x. It's calling, F2. So as you call F2, another stack frame for F2 is created here. So as you're calling functions, you're creating more and more stack frames. And as these functions resolve, for example, as you execute F2 and you return, then this stack frame is not used anymore. So then you would have actually only these three here on top as you go back to F1. As F1 returns, then this one is not used anymore. So then you have only these two. And then when you go, when F1, when main resolves, which is the end of the program, then all of these are, the main here is freed, okay? And then of course the program finishes and then the global variables are freed also. Okay. So here I'm providing you with a snapshot of the stack frame, the state of the stack as I'm executing main, this will create this, and then main is calling F1, this will create this, and as F1 is calling F2, it will create this. So essentially here, this is a snapshot of the stack as I'm currently executing this code here. If I would give you a snapshot as I'm here, for example, then I would have only these two stack frames, okay? Anyway, I'm sure that you saw that in some other courses. So you have the stack, that is the memory that is being consumed by the functions, basically the variables that are local to the functions. So that's why we call them local variables, okay? Then what is dynamic variables? So you have in C++ what is called dynamic memory allocation. In Java, you also have it, but not, you don't see that very much explicitly in your program. You actually have it all over the place in Java. But in C++, you can have only local variables. If you don't use pointers, then you'll have only local variables. In Java, even though you might think you're not using pointers, you are in fact using pointers because everything in Java is essentially a reference. If you are using pointers, such as, for example, this variable here is a pointer. f1x is a pointer to an int. If you are using a pointer and then you call the new operator is going to reserve memory on what is called the heap. Okay, so you have the stack and you have the heap, two different portions of memory. So essentially, we call new. It's making a call to the operating system to free a certain amount of memory cells in a certain memory area that was allocated to the process. Then this memory area is reserved, and then as you go, this new here is returning a pointer. New returns a pointer to this memory cell here, and then this pointer is assigned to this pointer variable, so which makes this f1x here point to this memory cell that has been allocated on the heap. So these are called dynamic variables, okay, or dynamic values in this case. So what's important to understand is that some people think that the entire pointer is residing on the heap. That's not true. There inside of f1 here, there is a local variable named f1x, which is of type pointer to int. This variable resides on the stack frame of f1, but it points to a value that is stored on the heap. Okay, that's something that sometimes people get confused with. So dynamic variables, they are variables that point to values on the heap. If you use dynamic variables, you must use pointers. The time you use pointers, this is defining dynamic variables. One of the difficult things is that in C++, in Java, you are actually doing that. Anytime you declare a variable in Java, it's actually doing exactly the same thing as I'm saying, except that the whole memory allocation and especially deallocation, memory deallocation is done by your garbage collector, your good friend, the garbage collector. In C++, you don't have this good friend, the garbage collector. Who is your good friend that is going to deallocate the memory that you have allocated using new? It's yourself, the programmer. If you don't do it correctly, the memory is going to keep being reserved on the heap. Thus, you would have what is called memory leaks if you don't yourself delete these or free these memory cells that were allocated by your program. So yes, avoiding memory leaks, very important aspect of C++. The compiler, the runtime system is not going to tell you whether or not you have memory leaks in your program. You may think everything is fine with your program. It may be full of memory leaks and you don't know. So it's very important that you yourself as a programmer know how to detect your potentially your own memory leaks. Okay, dynamic variables, if you use pointers, reserves memory on the heap. Local variables, these are the variables that are allocated on the stack for each of the functions that you execute. These are all local variables. These are local variables. However, this is here a dynamic variable or a pointer variable that is pointing to a dynamically allocated value, you might say more correctly. Local variables are not dynamic. If you declare a certain variable here, you don't have yourself to free it. As soon as the runtime system is gonna, for example, when you come inside here, it reserves a value, a memory cell for P, reserves a memory cell for F1. As soon as F1 returns, then these become out of scope. They're not specifically deleted, they're not freed. It's just that your stack pointer now points to here instead of pointing here. So the values will still be here, but then they will be reused later when you call another function, okay? But anytime you reserve something here, the thing is that if you make this here, if you execute this int star f1 x is equal to new int 10, then it's going to create this f1x here. The new is going to create this here, and then the new returns a pointer, which is assigned here, which makes this point here. And that's what happens when f1 is executed. If you return from this function f1, then this here ceases to be accessible. And then you go back to be here in the main function where this is accessible. Okay. Now what just happened is that this pointer that points here is the only thing that would allow you to free this memory. You can free the memory by calling delete only if you have the address of this or the name of this variable, okay? If you lose this pointer, then never are you going to be able to delete or to free this memory cell here. So here it goes and creates new, allocates this, and then return. Never called delete. So that means this thing here is forever going to be reserved in the computer's memory as long as this process is running. If I'm calling F1 repeatedly, which I'm doing in this for loop here, every time I'm going over another iteration in the for loop, I'm reserving another memory cell, another. So imagine I would do this for 1 billion times, then eventually the program would crash and say you ran out of heap memory. Okay, so that's why, of course, in many cases when you run a small program, there might be small memory leaks, not that much of a problem. But if you're running like an operating system that stays on forever and has infinite loops that are always doing the same things, monitoring things and so on, forever, and that in every iteration of this forever iteration, you would have a memory leak, then very quickly your operating system would crash. So yes, memory leaks, sometimes they're not that bad, but in general, it's very important to be aware, at least, that you have memory leaks. Okay. Okay, I already said that. Okay, so how do you dynamically allocate a value to a pointer by using the new operator? Okay. So when you use the new operator, as I just said, it returns a pointer to a value that's been reserved into the stack. So when you call new here, it returns a pointer to this value here, which is of type int. Then when you assign this pointer to this pointer value to this pointer, then you make the f1x point to this value here, this new value allocated on the stack. So anytime you use pointer, you have to use new to, and inevitably the value is going to reside on the stack. The value created is a nameless pointer values. What does that mean? You see that here my values, they all have a name. So here I have 44, it's an integer named x. However, as far as this memory cell here is concerned, it doesn't have a name. It was created by new int 10, which does not have a name. So this is essentially a nameless value, okay? The way you can refer to this value is by creating a pointer that would point to it, that would itself have a name. Okay. So anytime you call new, it's allocating something on the heap. Sometimes the heap might be called a free store. I personally like or have a habit of using heap. How does this allocate memory? By interacting with the runtime system. As I mentioned before, you don't have garbage collection. In fact, you could run a very similar Java program, even though Java program would not use pointers. It would, anytime you're calling new in Java, that's essentially what it does, exactly what it does. Even though you don't use pointers, all the values that you are manipulated in Java are in fact pointers or references. It uses what is called reference semantics in Java. We'll see that later. You have either reference semantics or value semantics. We'll cover that in an upcoming lecture. Java actually allows you to, even though you don't know, it uses only reference semantics. In C++, you can use either value or reference semantics. The thing is that, of course, C++ does not have garbage collection. In Java, you allocate something. If it goes out of scope, it stays there in the memory that's been allocated. Every now and then, the garbage collector is going to come and sweep things and then free things that are not referred to anymore. Okay, very convenient, but also somehow time-consuming and kind of random. Because this garbage collector is not controlled by your program. It's controlled by the Java virtual machine. Okay. If you want to have a predictable program, you don't want to have this program that controls your program, which is essentially what is the Java virtual machine. It's a program that controls your program. If this program that controls your program starts doing things which are not part of your program, then the execution of your program is affected by these things that the JVM is doing, including the garbage collector. For those of you who know C, new is equivalent to malloc, and free is equivalent to what we'll see is delete later. So further examples. So here I'm declaring 2 pointers to ints. So then these are wild pointers. Why? Because they're pointing to whatever address happens to be to the address that corresponds to whatever value was already there in the memory cells as they were assigned to these variables. Then you might say P1 is equal to new int. Then that goes in the new goes in the heap, gets a memory cell, which is not initialized to anything, and then returns a pointer, which is then assigned to P1, which the pointer here is assigned here, which makes P1 now point to this integer value, or this memory cell that contains an integer value. If I say star P1 is dereferencing P1. Dereferencing means I'm changing the value of P1, which is now 42. The value pointed to by P1. The value pointed to by P1 is this here. I change it to 42. Then I can say P2 is equal to P1, whereas P1 and P2 are 2 pointers. So that's actually a pointer assignment. So I take the value of P1. The value of P1 is what is stored here, which is the address of this memory cell. I take this address and I put it into P2, which makes now P1 and P2 point both to the same integer value. If I go star P2 is equal to 53, so the value pointed to by P2, which is this one here, is now 53. So as we said earlier, now you have also changed the value pointed to by P1. Again, powerful, but potentially problematic or confusing. Then if I go P1 is equal to new int, then I go new int, reserve a memory cell here, returns a pointer. I assign this pointer to P1. I assign this pointer to P1 here, which makes P1 point now here, even though pointer P2 actually points to still to this memory cell here. Then I assign 88 to the value pointed to by P1. The value pointed to by P1 is this one. The value pointed to by P1 is this here. I assign 88 to this, so that now becomes 88. So it's essentially the same thing as I described before, except that now you have some things that are on the heap. It's important that you are aware that these things are on the heap. Okay, so if the pointers that you are declaring are of class type, then the constructor is involved, okay? So when you call new on a, for example, an int, then it's basically just reserving a memory cell of type int, and then if you give an initial value, it's putting the value there. Fairly simple. But if the pointer if the thing you're creating using new is a class type, then it's going to eventually call a constructor of this class. That's why it's important to define your own constructors. If you don't, then the default constructor will be created for you, as we will see later. So I might go my class star my PTR, a value named my PTR, which is a pointer to an object of type my class. That would be one local value, local variable inside the function in which this, this code is residing. Then I go my PTR is equal to new my class, and then using a 2-parameter constructor that receives a double and an integer. So this constructor is executed, creates an object, which is then put into these memory cells that is allocated on the heap. And then new returns a pointer to this memory area, which is then assigned to my PTR. Now my PTR is pointing to the object that is now on the heap. You can still, as we saw earlier, you can still initialize non-class types, so that here that may appear that you're calling a constructor. Here you were using the parentheses, may appear that using a constructor of int and may hint that int is a class. It's not. This is just basically, syntactically speaking, this was allowed for having homogeneity with this syntax here, okay? That does not mean that here there's a constructor that is being called. I refer to you the previous discussion on initialization that we had in the first video of this slide set. So where can you use pointers? Anywhere you can use a type, you can use a pointer type. So for example, you can have a function that receives a pointer to an int. You can even have a function that returns a pointer to an int. Okay. Anywhere you can have a type, syntactically speaking, anywhere you can have a type in a program, you can have a pointer to a type. So there are potentially some problems with using pointers. So it is, anytime you call new, it's asking the operating system, give me some new, some free space on the heap and give me a pointer to it. That's what's happening when you call new. Now, what if there's no more free space on the heap? In the earlier versions of C++, the behavior of that would be that if you call new and there's no more free space, then it would actually return a null pointer. We'll see that later. It's basically saying you receive 0 as the pointer somehow. So that was the behavior of earlier C++ runtime systems. So that's why if you want to check if there was no memory available, then you would check if p is equal to null. In all of the recent compilers, it throws an exception. So if you call new, it would eventually, if there's no more memory available on the heap, then it will throw an exception of type bad alloc. Okay, we'll cover exceptions much later. So if you wanna, so here, that was it about new. So you reserve memory on the heap. Now, how do you free the memory on the heap? Okay, So you would use, so you call new to reserve memory, you would call delete to free the memory. Now in Java, you don't have such thing as delete because the garbage collector will be responsible for that, okay? In C++, you have an explicit keyword that you use to free your memory yourself, okay? It's very important. The rule of thumb is if you have new somewhere to reserve memory for something, there should be somewhere else in your program delete to actually free this memory that you have reserved using new. So for every new that you have, there should be a delete somewhere. If you call new and there's no corresponding delete, you have a memory leak. Okay. It's not necessarily that new and delete will be in the same scope. That's why it can get confusing sometimes. So simply put, if you call new here, so this is potentially in a function here, you declare a variable of type pointer to int, you call new int, and you assign this pointer to p, do some processing with this integer, and eventually before you go out of scope, you should call delete p. It's also always good to actually assign assign null to p, okay? Because if you don't assign null to p, or do I have no, okay. If you don't assign null to p, let's see what happens. So you have p here, which is a pointer to an int. This is your stack. This is your stack. This is your heap. And then when you call new, it actually reserves a memory cell here and then assigns the value 5 to it. And then the new returns this pointer here, which is then assigned to your variable p, which makes p point to this value here on the heap, okay? Then you use, the program uses this value 5 and so on, potentially changes whatever. And then before you go out of scope, you should actually call delete on p so that this is actually freed before you go out of scope. Okay. If you call delete p, what it does is actually freeze this memory cell here. So it used to be something that was assigned to an integer by the operating system and so on. So this value 5 was reserved by the operating system. If you call delete, then it instructs the operating system to say, I'm not using this anymore. You may do whatever you want. It's now something that is not assigned, and it's now something that is free to use. The value is still there, but if another part of your program is calling new, this might start being used for something else, okay? But p is still pointing there. Delete is not affecting p, it's affecting the fact that this memory cell was in fact reserved. Delete is only unreserving this memory cell, okay? Still, p is pointing here, okay? The fact of the matter is that if you don't do delete p and p is equal to null, then, or let's say you do delete p, but you don't do p is equal to null. So this was reserved, and when you go delete, this becomes unreserved. This becomes free, okay? This memory cell is free to use. If it is not used by something else as a new operator is being called further, then p would still be pointing here and still would have value 5 if you dereference it, okay? Even though you deleted, this is free, but if it has not yet been used by something else, it's still going to contain the value 5. But if something else is calling new, and then this becomes allocated to something else, which puts, let's say, the value 99 here, Then if you try to print P, it's still gonna point here and gonna think that the reference value of P is equal to 99, even though this is the value of another variable that has now started existing in your program. So that's what is called a dangling pointer. Dangling pointer is a pointer that used to point somewhere that made sense, and then you call delete on this pointer, but you did not tell this pointer, now you point nowhere. That's why if you say P is equal to null, it is essentially telling, if you go P is equal, so P is now pointing here. If you go P is equal to null, it basically somehow puts 0 inside of this memory cell here. So this pointer is not pointing anywhere, okay? So that's for that reason that when you delete something, always a good habit to assign null to it, okay? Some people might say, well, that's additional processing that you're doing. That's not necessary. If you know what you're doing, you don't have to assign null. Correct, okay? But that avoids some problems because dangling pointers can be extremely problematic, you know, especially that sometimes they might hold the same value for some time, and then as new is called, and this memory cell is assigned to something else, then suddenly it start having values that don't make sense. So it makes sense for some time to use this P, still holds the correct value, but after some point in time, it starts having some apparently random values. So yes, dangling pointers, much problematic. Pointer arithmetic. We go quickly over this. So when you have a pointer value, you can actually have arithmetic operations on it. So here you have a pointer to an int, and then you go assign an array of int to this pointer. So here essentially you have your pointer to an int, which is d, and then you have this pointer here that now is pointing nowhere, and then at a certain point in time you will allocate it to an array of 10 integers. So this array of 10 integers here is now pointed to by d, okay? So d is now pointing to the first memory cell allocated to this array of 10 integers, okay? No. So pointer arithmetics is about, well, you know, there's a value that is stored here, which you might think of it as an integer value that represents a memory cell. Now, because this is a mathematical value, this is a number that is being stored here. You can actually increase this number. You can increase the value of this number, of this pointer. If you increase the value of a pointer, then what it does is that it goes to the next memory cell. So basically, it increases the value of this by as much as the size of each of the elements of this here. Okay. So that's what is pointer arithmetics. We'll come back to that in more details when we talk about arrays. So yes, when you have pointers, you can increment a pointer. That's another very typical use and powerful use of pointers in C++. Now, what if you want to declare a pointer that is a constant, or to have a pointer that points to a constant value? There's a lot of different permutations here of cases. Let's say you declare an integer x. So here you have all these permutations. So either, well, here you're declaring a pointer to an int that eventually is going to point to this x here. So these are all pointer to int, and they are initialized by the address of x, right? So this one here is a pointer to an int. P1 is a pointer to an int, nothing new here. However, what if you put const here? So now this is a pointer to a constant int. What if you put const here? So now this is a pointer to a constant int. A constant pointer to a non-constant int. So this int that is being pointed to is not constant. However, the pointer itself is constant. What does that mean is that you, for example, cannot increment the pointer. You cannot make the pointer point somewhere else. A constant pointer, you give it a value, it cannot anymore change where it's going to point. For example, this one, this pointer P3 would always be pointing to the memory cell of X because it's a constant pointer. And here you have a combination of the two. Here is you're declaring a constant pointer to a constant int. Okay. So here we go to back to the notions of void pointer, while pointer, dangling pointer, and null pointers. I've already explained that before, so I'm going to go briefly here. So what is a void pointer? Is essentially a void pointer is a pointer that's pointing nowhere. So as I was saying before, if you want to make your pointer here D, for example, if you assign it to null, then it's essentially, it's pointing nowhere. There's no arrow going here that makes it point somewhere else. So in technical implementation way, very often that would be assigned value 0. So that 0 is an invalid value, coded value. That means this pointer does not point anywhere. If you try to dereference a, I'm sorry, here I'm talking about null pointers, sorry. So let's go to null pointers then. Null pointer. If you have a null pointer, essentially you have this value 0 in the memory cell. That means this null pointer is pointing nowhere, okay? If you try, and the particularity of a null pointer, if you try to dereference a null pointer, this is leading to a runtime error, okay? Some of them can actually be detected at compile time. So let's go back. Sorry about the confusion. Let's go back to void pointer. Void pointer is something that we didn't see yet, okay? That's what was confusing to me. What is a void pointer? So for example, here declaring a void pointer as a parameter to a function. A void pointer is a pointer that can point to any type. So for example, here my pointer is named D, and it's a pointer to an int, okay? The type of this variable is pointer to an int. That means if I want to make this pointer point somewhere, this somewhere must be of type int. Okay. If I make this pointer here point somewhere which is not int, and it's detectable at compile time, compiler will say this is an invalid assignment. Okay. If it's not detectable at runtime, then it may make your program crash, okay? So all this to say, when you declare a pointer, it's always a pointer to a certain type. That's what we saw before. But you're allowed to declare your pointer as a void pointer. That would mean that this pointer now can point anywhere. Anywhere you want, this pointer might point there. That this makes it, of course, a very abstract and powerful notion. However, there's a very heavy however here, is that every time you want to use it, if you want to dereference this pointer, you have to cast it into a specific pointer type before you can dereference it, okay? So yes, very powerful, but when you want to use it, you have to be very specific, okay? So that's a void pointer. And you have the notion of while pointer. So let's say you go in your program, you go int star D semicolon. So that would be a pointer to an int named D, and it's now pointing where? it's pointing wherever is this address, this number that is inside this memory cell here is making it point to. Because it was not initialized, it's now pointing to wherever address corresponds to the value that was there before this memory cell was assigned to this pointer. So that's what is called a wild pointer. It's potentially pointing somewhere where it doesn't make sense. It's even might be illegal to point there. Okay, wild pointers are very problematic because if you try to dereference them or use their value or do some operation with their value, it can lead either to a segmentation fault, which means that this pointer was pointing, for example, in the memory space of another process. It could also be pointing it to the memory cells assigned to your own program or somewhere where it's not illegal, in which case this pointer would actually be containing an arbitrary value. So yes, so wild pointers, they are as a result, in most cases, of declaring a pointer and not initializing it. Dangling pointer, I just explained that. Dangling pointer is when you use new, and then you make it point somewhere on the heap. Then you call delete, which frees this thing here, but still your pointer is pointing to that thing here that has now been freed. Okay, so dangling pointer, it's been assigned to somewhere which makes sense, but delete was called. Now it's still pointing there, and this thing, these memory cells may be used later on for something else, which will result in arbitrary value being present in this memory cell as far as this pointer is concerned. No, pointer. Okay, so then references. References, what they are, I'm going to go briefly over this. Reference, essentially what a reference is it's some kind of a constant pointer. Okay, it's a pointer for which you cannot change where it is pointing. It is in fact more than that, and that's why I'm not going to explain all the details of its implementation, because there's a lot of things being said here. A reference is also some kind of alias to another variable. So when you define a reference and you say this reference is equal to a certain variable name, then this reference becomes another name for this variable. Okay, and then you cannot assign this reference again. You cannot make it point to another variable. So pointers are very powerful because they allow you to point to the value of another variable. And that's also becomes problematic because then you can assign this pointer to an n number of variables in time. You can't do that for a reference. As soon as you allow a reference to be an alias to a variable, it is now forever bound to this memory cell. It's now forever an alias of the same thing that it was assigned to. As we'll see as we go, there's lots, some of the disadvantages of using pointers that, like for example, there's the star operator, there's the ampersand operator, as we'll see later, there's the arrow operator if you're using objects and pointers. There's a lot of very specific syntax that is involved in using pointers. If you use a reference, you're essentially defining an alias. So if I have a variable named an int I, and then I define a reference that is an alias to this one, then I basically use it as an int, okay? So as you use references, you use them as exactly as the type that they are being a reference to. So again, not going to go into all the details here. Even there are some examples here. I would invite you to go to the lab to actually cover these examples in more details, okay? Not that they are very complicated again, but it's helping you to understand what's the notion of a reference. There's terminology involved in a reference. The reference is an alias to a referent. So if you declare a variable let's say you declare this variable here refer to, and then you declare another variable x, which is a reference. So this is a reference to the referent, which is referred to here. So in fact, when you declare this variable x here, which is a referent, then anytime you use x, you are actually using refer to. So if you assign to x, you actually change the value of refer to. Okay. If later, for example, here you go x is equal to y, so it may appear that you are assigning another you are making x point or being an alias to something else. No, that's not what's happening here. What you are saying here is that x, which is an alias to refer to, is the value of x is now equal to the value of y. Okay, here you did not reassign a new referent to the reference x. You took the value of y and put it into x, which is an alias or a reference to refer to. So you see what I mean here. It's the same concept as a pointer, except that it's rather an alias, and you cannot change where this pointer is pointing to after. Can also allow you to, if you, for example, are passing by reference, then as you pass, for example, here you have this function here that is called, it's using x, then you call f2 of x. f2 is defining its parameter as a reference parameter. So essentially, as you pass x onto f2p, f2p is now an alias of x. So if here you change the value of f2p, you're in fact changing the value of x in this other scope. What's more, even then, in this, you might think this is weird. Yes, it is, but it's very convenient sometimes. You might be telling me when, but this is what it is, and here it goes. So here you see that this function f2 is returning a reference, okay? And what it is returning is in fact f2p. So f2p, if you remember in this case, f2 is passing x. The call to f2 is receiving x as f2p. So f2p is now a reference to x, but it's also returning f2p as a reference. So in fact, this f2 of x is itself a reference to x. So what this allows you is, because f2 of x is a reference, it can be assigned to, because you can assign to a reference. All this because this function returns a reference, which is something you can assign to. So what this allows you is to, if you say f2 of x is equal to 3, which seems to be nonsensical, but it makes sense because f2 of x is defined as returning a reference to an int. So if you go f2 of x is equal to 3, so that in fact passes x into f2p. Now, f2p is a reference to x, which will then increment f2p, which will increment x, and then you return f2p. So you return a reference to x. So that basically means that this here is actually a reference to x, and then you put 3 in this reference to x, okay? So you see that references can be used for very interesting things. And in fact, as we will see how you overload your stream insertion operator, it's going to use this notion. So here's small pointers, might seem related, but I decided to cut the presentation here. So see you later.